See, one of the things which you must understand in robotics is that nobody is ever going to pay you to make a parallel manipulator or a serial manipulator ab initio like this, right? That's done. But yes, you might be making another one for a company somewhere. But most of the work that is done in robotics is related to working on unusual systems, okay, not regular systems. You'll not, if you're not working on automobile part, you're not working on a cell phone part. So it's basically non-consumer electronics. So that's a rough definition of robotics. So essentially you must be agile, and so the idea is to kind of show you how you can get, you drag things from different branches of mathematics and sometimes physics, you patch it together to solve a problem on hand. Okay, so so I come back to this picture which you supposed to have seen, well, supposed to remember from last time, but there's some questions which you never asked me in the last lecture, right? So what is the question you didn't ask me? The question you didn't ask is, when I wrote this equation, how come I only have expressions in 3 unknowns, P12, P34, P56? How do I get Q1, Q2, so on and so forth? Now, if you go back to this, when I want to write the norm of P1, P2, I am basically writing the length of this side. Okay. So that has to be equal to L13 because this is fixed. Now how do you get it? You start with a coordinate system which is fixed to the base somewhere. You write a vector from here to here. Now that is known. It does not change. Okay, well, it does change depending on what the exact triangle which has been formed. But you remember the triangle, right? Do you not remember the triangle? You remember the triangle at least. But that triangle you can calculate. So, and then the perpendicular from this top point P1 to this, that you can calculate. So that is known. So what is not known is actually the inclination of this triangle, and so the inclination of this line P1, Q1. So now when you write this, the vector from here to here is known at this instant. Now then from Q1 to P1, you write it in terms of this magnitude R1, which is known at this instant, what you do not know, and then there will be two components along U1, which will be the cosine terms, and then along V1, which is the sine terms. So sines of P12 and cosine of P12 enters into the picture for P1. Similarly, P34 will enter into the picture for 3. And so that's why when you write the norm, you get terms involving sines and cosines. Okay. So you get this expression for this one for P1, P5, and the third one for P3, P5. Okay. So you get these 3 equations. Now we already discussed that we are doing this half angle substitution because we know that sines and cosines are very closely related, right? And then if you use the half angle formula, then it becomes essentially expression in terms of T12 and expression involving square of T12, right? Do you remember what cos theta is in terms of tan theta by 2? Why? 1 minus and then sin theta? Remember the formula, right? Okay. So that's why starting with this you will get all the expressions. Now if you look at, if I go back to the first one, so I have cosine of this, cosine of this, cosine of this, sine of this, so you'll have all the products sitting there. Okay. So you will have expression involving tan squared P12 by tan squared P12 by 2 you will have expression involving tangent of P12 by 2. But note carefully that there is no cos P12 being multiplied by, is there a P12 being multiplied by sin P12? No, right, and cos P12 square is also not here in this expression. So that is important, the detail is important, and that is why you end up getting equation in this form. So maximum you will have is square power of 5, 6, and then A and B and C will contain terms involving T12 and T34, but there will be more complicated terms. And what we discussed is, and so these are in this form, A, B, C, they are second degree polynomials in T12, okay, and RST are second degree polynomials in T34, that you can expand out. So you simply take, you had two equations and we said there must be at least one root T56 which is common. So each of them will have two roots, two solutions to T56, but at least one of them must be common, right, otherwise we are in deep trouble. We realize that each one of them can have two roots, both of them do not need to be common, but at least one has to be common because physically the manipulator is in one posture. So physically one angle must be the same, other one, because we have squared, we have taken tan, half angle, all kind of funny things can happen. So we are not sure of that, but at least one must be common, and if it is there, then this resultant D must be equal to 0. Now let us think about the nature of the resultant D. So what will it contain? It will contain products of A with B. To find the determinant, what are the kind of terms which we will have? It will contain products of A with B and that multiplied by C, or A with B and that multiplied with S, or R multiplied with S multiplied with T. It will have these kind of terms in it, right? And if you look carefully, will you have any place where 4 of these terms get multiplied? Okay, so that helps us. So if you expand D out, you will get expression which is in this term, this type, G times T34 raised to the power of 4, T34 raised to the power of 3. So these terms G, M, N, U and V, they will all be fourth order polynomials in T12. Okay. Generated one polynomial in T34. Now we go back to this equation, P1 minus P3 minus L13 equal to 0. Now this one took two of those equations, eliminated 1, 5 from it, so I ended up with just 3, 4, and then I took the other equation and I know that is already 3, 4 and 1, 2, so I again land up with two equations, right, which are different, they are not the same equation written in two different ways, except that these are second order polynomials in T12. So you say that I must have one root of 3, 4 common between the two, so you form this larger resultant. Now what is the order of this polynomial? These are fourth order, so worst case you multiply G and M and then this and then this and then this, so you will end up with a polynomial in T12 of the order 16, okay, the roots of which will give you T12. So if you know T12, you can go back and solve for 3, 4, 1, 5, anything that you want to do. So there are 16 possible solutions to T12 because it's a 16th order polynomial. Okay. Now, the next interesting part is that if you look at these expressions carefully, if you did evaluate them for the TSSM, then D1 will only contain even parts of T12. If you expand, so now, so it tells you something which you can guess fairly intuitively, that if I give you the leg lengths, with the same leg lengths you can assemble the platform on top, and you can just flip the leg lengths below, you can also assemble the platform at the bottom. Right? So mirror solutions are allowed in this case. Okay. Now in this case it is allowed because you have taken the base and the platform on top both to be plane. So when you have 6 points at the base, it is not necessary that they lie in a plane, but in this case you have essentially effectively only 3 points. So 3 points always have to lie on a plane, you have no choice about it. So that is the advantage. So you then through that you are creating the axis of symmetry. So if you have 6 points, you need not have them in a plane, so then you may not have the symmetry. So each solution, each configuration has a corresponding mirror configuration with respect to the base, and but you can see that if the symmetry goes away immediately, that you can have at least 16 solutions you can have for the direct kinematics of the parallel manipulator. So if you just manage to take the symmetry away, then you will at least have 16 solutions. But what we do not know is that, based on the work we have done on the TSSM, that whether 16 real assembly modes exist, right, or even if the 8 assembly mode which I am saying, roots of the polynomial, there is no assurance that they are all real. They could be imaginary, in which case, I mean, you can assemble it imaginary, but physically you may not be able to assemble them. That we have not tested so far. Okay. And so that is because once you go beyond 4, you cannot say, you have to only solve them numerically, right. And how do you solve polynomial numerically? Newton-Raphson.
First you find an interval in which there is only one zero crossing and Newton.
First you
Find an interval in which there is only one
zero crossing. How do you find out there is only one zero crossing? Huh? Positive and negative, but then if there are 3 zero crossings in the middle?
Storm's method.
Oh. So very interesting methods for polynomial, like I said. So Storm's method, one of them. Then there is another thing called continuation methods. So if you want to have a 16-order polynomial, it's very, very simple actually, think about it. So what they do is, they just take a 16-order polynomial, so they start by saying x minus 1 whole square raised to the power 16. So there are you spread out the coefficients. Now what you do is, you just adjust so that is x minus 1, 16 of them. So you get a set of coefficients, so you adjust one of the coefficients first, so that it matches one of the coefficients of your polynomial. So you take suppose your 0th order thing there, the constant term was 34, right. So instead of multiplying x minus 1 into x minus 1 into x minus 1, the last one you multiply by 34. So it will fix the 0th order term. So then you adjust the second one to match the second, that one by one, you keep on adjusting them. So now when you adjust the second one, you have got to go back and adjust your first one again. But through this method, you are guaranteed to turn up with the right solution with all the right roots. So slowly you will converge to that. That's another method which is available. There are other methods in which you can find out, like I told you, how many solutions are there in each within a bound. So you keep shifting the bound until you find the only one in there, which is the zero crossing method that you are talking about. So there is a method for that. So but they are all essentially numerical procedures. So it's very difficult until the time you actually find the roots to actually comment whether they are real or they are not. Okay, so this is essentially then not a very practical method to do, but it can be done. But it is easier to find a polynomial solution of polynomial using iterative methods than to find solution to generic equations. So there is this nice command. Well, this is not a very nice command, it's just defining an array. Okay. So I just define array. There's nothing very great about it. So I should have actually taken, I'll take both of these together. So I define array called poly1 roots. So in array I put in the roots 1, 2, 3. Then I take a second array, I put in another root, so I have made one common root. And then there is this function called poly, which generates a polynomial coefficients for these roots. So when I feed poly1 root, so it takes the roots as 1, 2, 3, and if you look at this, it gives me 1, minus 16, 11 and minus 6. So these are the coefficients of the polynomial corresponding to the roots which I specified earlier. So this is the second one. So this is just MATLAB, and then I create the Sylvester matrix. Okay. So let us see, since I created, now let's look at this. Well, I should show it here. You are familiar with this dot dot dot, right? 3 dot means a line is extended onto the next line. So that lets you format it very nicely. Now look at this way of assigning the arrays. So you can use an existing array, right? So I use poly1, so it takes in all the coefficients, puts it there, and then 0, 0. That finishes my row. So I am not writing all the coefficients out by hand every time, which is exactly what is there in the definition of the Sylvester matrix. So I am using the same format, so you can use all of this, okay, to simplify things. Okay. Is this clear? So you don't need to write out everything. So finally, it thinks a lot and gives me a wrong answer, right? But I can cut paste this and put it there. I think that's easier. Oh, there you go. Okay. So, oh, full screen. No, I can't do full screen. I have to keep going back and forth. But I can maximize this and I can maximize this. Chalo. So it's 2.5580 e to the power minus 12. Is that a wrong answer?
Close to 0.
Close to 0. And some people are not happy with it. So we will redefine our Sylvester as this. Now it will think harder and harder. Okay. My poor laptop working on the battery, and seems to give you the same answer, except that it has put some commas at different places.
Not symbolic.
Yeah. Right? That's all it seems to have done. But now if you do determinant of Sylvester, boom, and the answer is 0. Huh? What? Yeah. Okay, so if you're dealing with nice neat numbers and things like this, and so this works out very nicely because internally it takes care of many things. All these rounding offs are not done, so it actually does cancellations and factorization.
The coefficients are integers, right?
Yes.
In that case, MATLAB should ideally not have a problem because it does not internally round off. If you do 1 by 3, a is equal to 1 by 3 and then multiply that by 3, you get 1, not 0.9999, which is what you get straight to the calculator.
No, except that the number of bits of precision are much higher. 32 bit. No calculator has 32 bit.
It doesn't. But
Yeah. So that's why you don't see it. But this is a good example of the fact that it does it. This is a good example of the fact that it does it. See, it's a question of where you do the division. That's really the most important part in finding the determinant. Or I mean, whether you wait for the number to carry over. So if a number becomes more than 2 to the power 32, it will put it in that other form. I think it will carry on till integer until it becomes 2 to the power 32, which happens very rapidly. If you multiply, I think 60, 47, 12 and 11 or 60s, you're gone. Okay. So that's where, so the moment it converts, you reach the limit of 2 to the power 32, in fact not 2 to the power 32, 2 to the power 31 perhaps, because you need one bit to keep the plus 1 plus minus 1, right? So moment it does that, then it will convert. If you're not dealing with such large numbers, you'll be fine. So 1 by 3 into 3 by 1 is okay. That's not too many bits. Okay, so 2 lessons here. One is how to use some of the, so MATLAB has many functions which support these kind of polynomials, and so like this poly command, and there are many more commands which support it. Okay. So this is reasonably clear. So you think you can go back and do that? You can. Okay. So next is to show you that it is not that exotic. What I will do is, I will show you something even more base. Okay. So this is Excel. Okay. So we will do some kinematics using Excel. So this is for the LEA-like robot which I talked about. So you define roll, pitch, yaw, right, and then x, y, z. Now what is roll, pitch, yaw? Remember, it's the Euler 3, right, where rotations are about x axis, y axis, then the z axis, about the global frame. So for that there is a corresponding transformation matrix which you can look up. And so just to show you how this works, suppose I said roll, boom, everything is changed. Okay. So we can see the default state. So there is a little difference in the leg length. So I have said roll is 0, pitch is 0, only z is 300, so it's just flat platform up top. There is a little difference in the leg lengths. Okay. So that is because so this shows you how the points are attached at the top platform. This is just a top view. And this shows you how the points are attached in the bottom platform. Okay. So you can also plot them. Now in doing this, what I need put in as input is in the platform coordinates what are the positions of attachment at the top. So this is completely along the x-axis, first point is completely along the x-axis. So this is the first attachment point on the top, this is the second, so I have taken roughly a radius of 100 for all of them, and similarly for the base I have taken roughly a radius of 150 and I have spread them around. Okay. Now I have deliberately not put them at equal intervals, it is very tempting to put it at 60, 60, 60 and 6 of them. But if you do that, there is an inherent instability in the manipulator. Can you visualize that if all of them are 60, then if all the leg lengths are the same, then you can just twist the manipulator and just slowly start coming down as the sticks bend around. Can you visualize it, most of you? No. So you start with this configuration where you pull it up, right? So all the sticks will be essentially going straight here. Then as you twist, these keep getting displaced, so the platform will keep lowering and lowering. So that's a singularity. Okay, so we have not discussed the singularity for this one so far because it's funny. So I did not want to do that, so I deliberately staggered it. So now I've broken the symmetry on the top and the base. Now there is no reason, if I had this here, I need not have put this here, I could have put this here. Okay, you just need to break the symmetry, which would have been fine, but this is the lazy way of doing it. So I could have programmed this whole thing in MATLAB, but it's interesting to do it once in a while in Excel, okay, because it's always handy. You don't need to be connected to the IIT LAN to do that, right? You guys don't do that, right? So similarly you define the leg 2, so 50, 87, 87, 85, so you just define the top positions on all the things, then you define the bottom attachment points and all of them. Okay. So
it is not taking Z into consideration?
Which? It is?
The leg coordinates of the leg ends.
Coordinates of?
So like Px, Py, Pz and Bx, By, Bz.
Yes.
They are the coordinates of the end points of leg 1, say.
Yeah, at the bottom, yeah. So I'm assuming they're all in the single plane.
So the base and the upper part are in the same plane?
No, because if you remember, this is given in the base coordinate system, this is given in the platform coordinate system by the original definition, because I'll then multiply it with the transformation matrix to move it down to the base coordinate system. Okay. So that is what is done. I'll just get the relevant page out here. There you go. So now all I need to do is I need to code this equation to get the x coordinate of the top in the base frame. So that's quite simple, you just need to write this. Why is it not showing the, there you go, nice equation, right? Can you see this equation roughly, right? All the causes and sines written in there. So similarly you do this and you do it, but you need to do it for only one leg, because after that you can just copy this, paste it here, copy it, paste it here, copy it, paste it here, and Excel nicely takes care of looking at the appropriate data from the other side and backing it out, right? Okay. So then there is a very simple formula for the length. So you get all the lengths. So this is your inverse kinematics. Okay, no problems. So now we have to define the, so inverse kinematics was very nice using this, there's no problem with it. So next thing we have to look at the screws. So How do you get the screws? The screw has to be lines which are along the length of the legs, right? So, and then see, but the length of the leg, I usually want a vector which is in that direction, right? So, you take the corresponding terms and you have to divide it by the length which I am doing. So, E15 is this one, this element. Okay. So, similarly for the other ones you keep dividing by the E15 to normalize that. This one is a more complicated expression. So, here you are simply doing the cross product. Okay. So, it is not too bad. You just write the cross product, remembering that you are doing the cross product with a vector which is from the line to the origin. So, you have to minus it out essentially. So, you can write the vector, then you can obtain the, then you simply stack these and you obtain the screw of the Jacobian, right. Then you can find the Jacobian. So, there is a nice command called transpose, right. There is a nice command called transpose which is available. And if you look carefully, is it visible at all? So, there is this little curly brace here, right. So, you guys should sit in the front row so that you can see the little curly brace. Can you see the curly brace? Can you see the curly brace? You can? Oh. Okay, good eyes. At my age you can't. Now, the curly brace is because what is the transpose function? You are taking a function, you are taking this matrix, right, and I am transposing it. So, it's, and then the result that you get as a consequence of this spreads over a 6 by 6 box. Okay. So, these are called array functions. So, to do an array function, what you would have to do is you write equal to transpose and then you pick up the zone E24 to J29 like you usually do in Excel, and then once you are here, you got to hit Control Shift Enter. That is called an array function. So, that is what gives you arrays. It's used for a huge number of tasks in Excel, including finding histograms and doing this kind of activity. So, you can get that, and if you are interested you can find the determinant, right. If you are interested you can find inverse of the Jacobian, okay, there is a metric inverse, and then you are the boss, right. Obviously you can find you can set target L's and do delta L's and you can figure things out, okay. So, Excel is actually a fairly powerful engineering tool. It has got many of the capabilities of MATLAB built in. Have a good midsem break and figure out how to do these kind of things in